Back to the main chassis, which I'm in the process of cleaning. While I have easy access to all of both sides of this main circuit board, I want to check the electrolytic capacitors. These are components that can dry out over time, and this can cause either complete failure or degradation of their performance, so it's not an unusual problem to find in older equipment. To that end, I've disconnected one lead of a small randomly selected collection of these capacitors, and to start with I'm going to use this multimeter to check their capacitance. First of all, this one over here, which is labelled 47 microfarads. $52.5. I'm sure that's going to be within specification. Electrolytic capacitors generally have a fairly wide tolerance. Let's try this one here, which is labelled 33. $39, that's fine. Move on to this one, which is marked 15 microfarads. $19, that should be acceptable. And one more, which is marked 4.7 microfarads. A bit difficult to get the test clip in here, I just have to hold it in contact. 6.7, that's fine too. Now I'm going to use this cheap and cheerful ESR meter to check the internal resistance of these capacitors, because a problem that can be caused as they dry out is that they develop a high internal impedance, even though their capacitance is still about what it should be. The precise value this meter displays isn't particularly important, but it should be fairly obvious if a capacitor has failed, because the reading will be much higher than it should be. It's proving difficult to get the connector in here. Here we go. 0.4 ohms, that's absolutely fine, nothing wrong with that one. One and a half ohms, I think that's good too. Physically smaller capacitors and capacitors with lower capacitance generally have a higher ESR value. $1.4, that's fine too. This one over here might be difficult to get the leads in place again. It's difficult to get the test lead in place, but I'm sure I have made contact, and I can't get any reading at all. Here's the offending component. An ESR over 60 ohms is certainly far too high, so this component has dried out or developed some other fault. So I'll replace this one. However, given that it's the only 4.7 microfarad capacitor on the board and the only one as small as this, and the others I checked didn't indicate any problems, I will leave the others. If I'd found some others with faults, I would probably go ahead and replace every electrolytic capacitor in this instrument. I was curious about the purpose of the failed capacitor, so I found it here on the parts diagram. It's this one, C1210. and here it is on the circuit diagram up here. It's labelled 33 microfarads, and in the service manual parts list it's labelled as 15 microfarads. However, the capacitor I've removed is marked 4.7 microfarads, and I assume this oscilloscope was working properly at some point, so that's what I'll replace it with. I've not fully deciphered this part of the circuit, but it's part of the main time base circuitry, and I think it's involved with generating the ramp waveform that drives the trace from left to right across the CRT. I've refitted and reconnected the front panel control assembly and confirmed the exposition control over here no longer causes a short circuit, so I think it's time to try turning it on again. I've got a signal generator feeding a 100 kHz triangle wave into channel A. Thankfully that's still working, and the controls seem to operate a bit more smoothly after cleaning. Let's try channel B. Switch triggering to channel B. This is where we had a problem before. It would not trigger from channel B. At least I think that's the cause of the problem. Certainly I think the signal from input B is reaching the Y direction deflection plates of the CRT, because adjusting the input attenuator does change the amplitude on the display. Ah, that's interesting. It's triggered now, and I've done that by pressing in both the A and B channel trigger selections over here on the main time base, and that's labelled composite triggering. I believe that looks at the signals on both channels and can trigger from an event on either. The problem appears to be only when channel B alone is selected as the trigger source. I've been investigating the main time base circuit, and in particular the trigger generation and trigger selection portions of it. As expected, there's only one trigger generation circuit for the main time base, but the source that's fed to it is selected according to the settings of the front panel controls. As triggering works in at least most or maybe even all cases apart from when channel B is selected, then the trigger circuit must be working properly, but there's a problem either with the switching or with the source of the trigger signal when channel B is selected. You're looking at the underside of the circuit board that houses the trigger source selection switches and the input switching. And here's the diagram for that circuit board in the manual for the PM3214. It didn't take me too long to notice that they're not a perfect match, and one of the most obvious differences is that these two switches here are shorter in this diagram than on the circuit board. A little bit more investigation revealed that there are at least two different variations of the PM3214. In the one that this diagram is for, these two switches select either external triggering or line triggering, which means synchronization with the mains frequency, provided the oscilloscope is being powered from the mains. But on the version I've got, this switch selects external triggering, This switch selects external triggering 2, but with the amplitude of the input divided by 10. And for line triggering, both of these switches must be pushed in together. I then found this diagram here, which comes from the PM3217 service manual, which is a different oscilloscope in the same family, and this board exactly matches the one in this oscilloscope here, the PM3214 that I've got. Furthermore, other aspects of the diagrams and descriptions in the PM3217 service manual better match the PM3214 that I've got. For example, here's the main circuit board layout diagram for the 3214 that I showed you earlier. It certainly allowed me to locate a number of components, however there are some differences. The version of this diagram in the PM3217 service manual seems to be a perfect match for the oscilloscope I've got, though of course I've not checked every single component. I suspect there were either at least 2 revisions of this family of oscilloscopes, or perhaps the PM3217 was developed slightly later, and from that point onwards, versions of the 3214 were manufactured using the same circuit board. Let's have a look at the sources of the trigger signals that arrive at these points here. These two circuit sections process the signals for channels A and channel B. The signal flow is from left to right, and the outputs up here and here go onto a circuit that selects one or the other to feed to the CRT's Y deflection plates. The signals fed to the trigger circuits are taken from the collectors of these transistors here and here for channel A, and here for channel B. So for example, this point here is used to extract the trigger signal used for the main time base when triggering from channel B is selected. So this point is connected to here. And when the switches are set for triggering from channel B, this point and this point are switched down to 0 volts by these two switches, and these switches are set so that the channel B signal passes through here, up to here, through these switches, and into the input of the trigger circuit, the rest of which is off to the right hand side of this page. This bit of circuit here receives the signals from channels A and channel B from the outputs on the diagram I showed earlier. They arrive here and here, and it then selects one or the other at any particular instance to pass on to the CRT's Y deflection plates. The composite trigger signals are extracted at the collectors of these transistors here and here, one again for the delayed time base and one for the main time base. So the signal used for composite triggering is the channel A or channel B signal, whichever happens to be being sent to the CRT's Y deflection plates at that particular time. These are the 4 transistors, the collectors of which supply signals that can be switched to the trigger inputs of the 2 time-based circuits. I've already verified there's connectivity between each collector and the appropriate switch contact on the front panel PCB. This one on the left is V512, and it supplies the signal that can be switched from channel A to the main time-based trigger input, and this one on the right is V612, and it does the same thing for channel B. The oscilloscope's on, and it's displaying a 100 kHz triangle wave via channel A. Let's have a look at the signal present on the collector of V512. It's of rather low amplitude and it's not very stable, but I think it's the signal being fed to channel A. Let's confirm by switching the signal generator to change the wave shape. Now it's a sine wave, and now a square wave. Yes, that signal is clearly being derived from the input to channel A. Switch it back to a triangle wave. Now if I switch the main time-based triggering to trigger from channel B, this signal should disappear because the front panel switch will switch this point down to 0 volts. And that does seem to be what has happened. Let's see now whether we can pick up the same signal at the collector of this transistor here, V612. If I move the input connector to channel B, leave the triggering set to trigger from channel B, and switch the trace to show channel B. So I can now see something on the front of the CRT, but as usual, it looks like the input waveform, but the oscilloscope's not triggering on it. Nothing. I suppose I'm not too surprised by that. This is the base of transistor V612. Yes, we can clearly see the channel B signal is present there. I verify by once again changing the shape of the waveform. So I would think that either this transistor or one of the components immediately connected to it is faulty. I've removed transistor V612 from the socket on the right, and a simple check with a multimeter in its diode test mode does suggest it's faulty. It measures open circuit between its base and emitter and between base and collector, even when a voltage is applied that should cause those junctions to conduct. I've also tested the remaining three, and there doesn't seem to be anything wrong with those. So I'm going to try moving this transistor that supplies the channel B signal to the trigger input for the delayed time base over to this socket on the right, where it should be able to do the job for the main time base. Here it is displaying a signal via channel B, and the triggering seems to be working now. I have noticed that if I switch the triggering to DC mode, it's in auto at the moment, I can't get it to trigger by adjusting the trigger level control. But I can if I move it over to channel A and switch the triggering to A. It's on auto. Switch to DC triggering, adjust the level control, and there it is. I'm hoping this problem is simply due to poor adjustment somewhere. I've replaced the faulty transistor with a BC557B. I'm not sure whether that's necessarily a good replacement. Its specifications are rather different from the original. However, its voltage ratings are similar, and that's the main reason why I selected it. I've installed it in position V611. That's the transistor that provides the channel B trigger signal to the delayed time base. And it seems to work. With various test signals connected to channel B and the front panel switches are set appropriately, the delayed time base does trigger as I'd expect it to. So unless further testing indicates any problems, I'll leave these transistors alone. While testing, I've noticed these 4 transistors here become rather hot. Given their type, that's possibly normal and not too surprising. However, I want to investigate this part of the circuit to make sure the increased temperature isn't an indication of a fault. The 4 medium power transistors are part of the X deflection driver. Here are the temperatures I recorded using a thermocouple pressed against the side of the case of each after the oscilloscope had been on for about 15 minutes. I've checked the datasheets for all of these transistors, other than the BF338, as I can't find a complete one for this device. In all cases, the maximum permitted temperature is around 200 degrees centigrade, and so there isn't much risk of that being exceeded. However, should they be getting as warm as they do? V1417 and V1426 clearly operate as constant current sources. Each has its base held at a fixed voltage by a Zener diode. This in turn keeps their emitters at a fixed voltage, and the collector-emitter current is then determined by the 1.15 kΩ resistor connected from the emitter of each to the plus or minus 180 volt supply. I've measured these resistors in circuit and found them to have exactly the value stated. The diagram indicates the collector-emitter current should be 4 mA. Here are the voltages I measured at various points, using a multimeter set to its DC volts range. Starting near the top of the diagram, I measured about 4 volts across resistor R1441, and this means a transistor current of around 3.5 mA. With 84 volts between the emitter and collector of V1417, the power dissipated by this transistor must be approximately 300 milliwatts. Repeating the calculations for V1426 puts its power dissipation at around 400 milliwatts. The datasheet specified maximum dissipation for transistors like these is usually close to 1 watt. The datasheet for one of these states it has a thermal resistance of 150 degrees per watt between its junction and free air surrounding its case. Using this, along with the power dissipation values just calculated, and the fact that the room temperature was about 20 degrees centigrade, results in calculated temperatures for V1417 and V1426 very close to those measured. The temperatures will certainly become a bit higher once the case is refitted. Still, I conclude the temperatures of these transistors are as they should be and nothing to be greatly concerned about. However, I think an admirable design goal is to aim to keep active devices below finger-burning hot, and so I'll consider fitting heatsinks to the current source transistors if I can find any that will fit in the tight space. I noted that the voltages at points A and B are not steady, but rather vary as shown here in images captured from an oscilloscope. The diagram labels point C as being at 9 volts, and both multimeter and oscilloscope reported a steady voltage within a few millivolts of 9 volts here. The PM3217 service manual includes diagrams of the expected waveforms at the two connections to the X deflection plates. I found a perfect match in both cases, to within a minor division on the X and Y scales. A quick run-through of all the major functions with various test signals applied suggests this oscilloscope may now be fully functioning. The PM3217 service manual contains a fairly comprehensive set of verification and adjustment procedures, and I think most will also apply to the PM3214. So I'm going to read through them carefully and have a go at following them. I'll report back on any interesting findings.